In this video, we'll review the function concept and briefly look at some functions that we've already met before. A function is a rule that assigns to each input exactly one output. An example is given by the area of a circle. The area of a circle is a function of the radius of the circle, a relationship expressed in the formula A equals pi r squared, where A is the area and r is the radius of the circle. We often give names to our functions. Common choices are f for function, or g or h. So we could let the area function be called f. So f evaluated at r, the radius, is pi r squared, which is the area. We call the collection of all inputs the domain, and the collection of all outputs the range or image. So the collection of all inputs is the domain, which is represented here by a square. And the range is the collection of all outputs in this circle that we've drawn here. We draw the domain as one object which contains some points. And the range is a collection of points in this circle. The range is the collection of all outputs. We've labeled some of the points in the domain x, y, z, and w. Our function is called f, and as you can see, we have an arrow going from the domain to the range. F takes points in the domain and sends them to or maps them to these points in the range. So x is mapped to A or sent to A, y is sent to B, z is sent to C, and w is also sent to C. So it's okay if 2 points in the domain go to the same point in the range. Notice also that there are some points here that are not the output of the function. That's okay too. The function needs to assign an output to every point in the domain, but over here the range is the collection of outputs, but there might be some other points here which don't get included in that. That's fine. This set over here, the collection of all of these points, is known as the codomain, but the range is just the collection of actual images, the things that are actually achieved as a result of the function sending something from the domain over to where the range is. So if some points are left out, that's fine. And it's also okay that w and z get sent to the same point. For each point in the domain, you get something in the range. But it's very important that you only get one output for every input. A function is a machine. You feed it an input and it gives you exactly one output. And it should give you the same output every time you give it the same input. So every time I put in x, it should give me A. Every time I put in y, it should give me B. There shouldn't be occasions when I put in an x and it'll give me A, and then other occasions when I put in an x, it'll give me something else. If that happens, it's not a function. The function is a rule. For every x in the domain, for every point in the domain, there's exactly one output, which we're calling A in this case. So we write down f at x is equal to A, f at y is equal to B, f at z is equal to C, and f at w is equal to C as well. Again, it's okay that these two inputs give you the same output. The way we read this is f at x, which is shorthand for saying f evaluated at x. It's also normal to say f of x. Let's look at an example. This is the square root function. F at x equals the square root of x. In this case, the domain is the set of all non-negative real numbers, and that is also the range, the set of all non-negative real numbers. Every positive number has two square roots, a positive one and a negative one. So for example, negative 2 squared is 4, and positive 2 squared is also 4. So that means this number 4 has two square roots, positive 2 and negative 2. But a function can have only one output for each input. So that's why when we write down f at 4 equals the square root of 4, or radical 4, it has to be just one number. So we pick radical x to be the positive square root of x. And that's why the range is the set of all non-negative real numbers. Even though every positive number has two square roots, a positive and negative one, in order to have the square root function, we have to just look at the positive square root. So radical x gives you the positive square root. You have to make a choice. You can either look at the negative square root or the positive square root. So just by convention, we take this radical symbol to mean the positive square root. So radical 4 is just one number, the positive square root of 4. So f at 4, f evaluated at 4, is the positive square root of 4, which is 2. Now every positive number has two square roots. Of course, we also have the square root of 0, but that's just one number. The square root of 0 is 0. It's also possible to represent functions graphically. The graph of the function f is a set of ordered pairs. It's the collection x comma f at x, where x is in this set, which we call the domain of f. This symbol right here is read as is an element of. So x is an element of the domain of f. So this set is the domain of f. So when you see DOM like this means the domain. So let's just write that here. DOM of f is the domain of f. That's just another way of writing it. This symbol, which looks a little bit like an epsilon, and originally was an epsilon a long time ago, means is an element of. You can also read it as is a member of. So is a member of. So x is a member of the domain of f. So the domain of f gives you your input values. So you put the input value first, and then the output value comes next. So this is a collection of pairs, the input and the output. And this gives you a graph in two-dimensional space, as you can see here. So here we're graphing the square root of x, or the positive square root. So we often denote this by writing next to the curve y equals the square root of x. But what we really mean here is for any x value, the corresponding y value is the square root of x. So if we pick any point on the curve here like this, that gives us an x value, and the corresponding y value here, x comma y, well, y is the square root of x, the positive square root of x. The collection of all of these points, the input with its corresponding output, gives you the graph of the function, which we can represent as a curve in two-dimensional space. This leads us to something called the vertical line test. A curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve more than once. So here we actually have the graph of the equation x equals y squared. In this case, what you're looking at is not the graph of a function. If I pick an x value and then draw a vertical line, it may intersect the curve twice. Now, I say may because if I draw a vertical line for a positive value of x, you can see that it does in fact intersect twice. If I pick a negative value, so let's extend our x-axis here. If I pick a negative x value and draw a vertical line, that won't intersect the curve at all. So that doesn't give me a problem. I only get a problem over here when I have positive values of x. Even x equals 0 doesn't give me a problem, because if I pick x equals 0, there's only one spot where the vertical line intersects there, and that's at the origin at the point 0, 0. So that's not a problem. But if I pick an x value which is positive, so this curve is x equals y squared. The top half is where y is equal to the positive square root of x. The bottom half is where y is equal to the opposite, or the negative square root of x. So if I pick a positive value of x, I get two square roots, a positive square root and a negative square root. So what I'm looking at here is both of the square roots. So if you give me a positive number, there's a positive square root and a negative square root. And this graph isn't telling me which one I should pick. So if you have a function, then each x corresponds to exactly one y. But here in this graph, you can see that this x value corresponds to two different x values, one of them being positive and one of them being negative. So this doesn't represent a function, or this doesn't represent the graph of a function, because for each x value, or at least each positive x value, I can find two y values, two outputs. So what we're seeing here is just the fact that a positive number will have two square roots. And so in order to have a function, we need to determine which of those square roots we select. The top half of the curve is achieved by selecting our function to be the positive square root of x. If we want the bottom half of the curve, we can let our function give you the opposite, or the negative square roots. That also gives you a function, it just gives you a different function. But if you take both halves together, then you don't have a function, because each x corresponds to two y's. And that's what is exemplified by the vertical line test, because the vertical line test picks out every place on the curve where you have an x value corresponding to a y value. So for this vertical line corresponds to this x value. And when it crosses twice, like it does here, that means there are two different y values for that one x value. So if a curve doesn't pass the vertical line test, that means there's more than one output for each input. So that means it can't be a function. So this graph that you see here is not the graph of a function, because it does not pass the vertical line test. And any function will pass the vertical line test, and this one doesn't, so it's not the graph of a function. Let's look at something that is a function. This is a function that we call a piecewise defined function, and you can see that it's piecewise defined because it's defined in separate pieces. So there's a piece for when x is less than or equal to 2, and there's another piece for when x is bigger than 2. And we have a different rule for each one of these pieces. So when x is less than or equal to 2, the rule is that you take the input x and you give me as an output 2 minus x. And that's given by this, at least this part of a straight line here. This rule holds for all x less than or equal to 2, so it continues as well for x negative. It's just not appearing in this picture, because we can only look at a finite amount, but it continues on out this way. Now if x is strictly greater than 2, then we use this parabola. So we take the input is x, and we take 2 away from it, x minus 2, and then we square that. And that gives us our output. So the way you use a piecewise defined function, you give me an input, which is x, and then I look, well, is x less than or equal to 2, or is it bigger than 2? So I look at the rules here. The rules are, which rule you use is determined by where the x is. So you look at your x and you ask, well, is it less than or equal to 2, or is it bigger than 2? And if it's less than or equal to 2, you use the rule corresponding to that, 2 minus x. If x is bigger than 2, you use the rule corresponding to that, which is x minus 2 quantity squared. And that tells you which rule to use. Lots of functions are piecewise defined, even familiar functions. For example, the absolute value of x. The way you think about the absolute value of x is you think about it as giving you the distance away from 0. In terms of the graph has this V shape. The output depends on what the input is. If x is positive or 0, then the output is just x again. I give you an x which is a positive number or 0, and you just give me x back. On the other hand, if x is negative, then you return to me the opposite of x. When you read this, it looks like negative x, so you think, oh, is this a negative number? No, it's actually the opposite of x. So when you see this symbol, you should read that as the opposite of x. And when we say opposite, the opposite sign. So if you give me a negative number, something over here, so x is less than 0, then you return to me the opposite of x, the opposite sign. So x is negative, so that means the opposite of x is necessarily positive. So if x is greater than or equal to 0, you give me back x, which is positive. If x is negative, then you give me back the opposite of x, which is also positive. So the output will always be positive. That means the y value is always positive, and as you can see in this graph, the y value is always positive. This graph does pass the vertical line test, because if I pick any x value and draw a vertical line, it will only intersect at most once, whether it's positive or negative. It only intersects once, exactly once. So this is the graph of a function, and it's the absolute value function. Absolute value signs often give you this piecewise defined behavior. As you can see in this example, h at x is the square root of the absolute value of x. The domain of the radical function is the set of all non-negative numbers, so you can only put in something which is 0 or positive. Now, x itself might be negative, so that's why I've put the absolute value signs around x. So now I've got a function which has domain the entire set of real numbers. You can give me any real number you want, and it will give me an output. I can see from the graph that this does pass the vertical line test. If I draw any vertical line, it will intersect at most once. So it is the graph of a function. What does it look like? Well, if x is positive, or 0, then you use the first rule, or the top rule, which is just radical x. So that's the positive square root. So this right here, this is y equals the positive square root of x. Now on the other hand, over here, if x is negative, then you return the positive square root of the opposite of x. So this graph right here is y equals the positive square root of the opposite of x. Now remember, on the left side of this graph, x is negative. So the opposite of x is a positive number. So it's a positive number. That means it makes sense to ask for the positive square root, which is what you see here. Now notice that this left portion is the reflection of the portion on the right through the y-axis. This is a common thing when you're dealing with absolute values. Symmetric about the y-axis. Functions that are symmetric about the y-axis are called even functions. Let's talk a little bit about symmetry in graphs. The first one we've already mentioned. An even function is symmetric about the y-axis. So that means if you reflect the curve through the y-axis, you get the same image, as you can see here in this curve, and also this curve here. This first one is y equals x squared, and this second one is y equals cosine of x. These two functions are what we call even functions, and they're symmetric about the y-axis. The defining property of an even function is that f evaluated at the opposite of x is the same thing as f at x. So in terms of the graph, what that means, you can think of the minus sign as telling you to go to the left. So if you go to the left x units, you get the same output as if you go to the right by x units. So moving towards the left, you'll get a certain shape, and moving towards the right, you get the same shape going towards the right as you do going towards the left. So if you take the opposite of x, so if you go to the left x units and look at the output, it will be the same as going to the right x units and looking at the output. We also have something called an odd function. The previous example was even, so this one is odd. An odd function is symmetric about the origin, as we say. So that means that if you rotate by 180 degrees around the origin, the point 0, 0, you end up with the same image. And you can see that here with these two images. To demonstrate that, let me just highlight this curve here. Now you can see that I've just drawn over the curve. And now the next thing I'm going to do is I'm going to select it. So I'm going to select it this way. I want to make sure that it's exactly the same or close enough. Now I'm just going to rotate around the origin like so, and you can see that I end up with essentially the same curve. It's a little bit off, but that's just because my original drawing was just a little bit off, as you can see. It's not perfect. We can do the same thing with this curve here. So again, it's not exactly perfect, but you can sort of get the idea there. And then we just select it like so. We have to make it exactly the same amount on the left as the right. There we go. And then we just spin it around, and there we go. You see, I was a little off, but there we are. There we have it. So if you take the curve and rotate it 180 degrees around the origin, or the point 0, 0, you end up with the same image. Now in this case, the defining property is what you see here. It's f evaluated at negative x is equal to the opposite of f at x. So again, you think about this as giving you the direction. So if you go to the left by x units and you put that into your function, that's like the going to the right by x units, but then going down instead of up. So we're this negative sign here, so the negative sign inside the parentheses indicates that you're moving left. Now outside, this negative sign outside of the f of x, that indicates you're going down instead of up, or up instead of down, you're just changing the direction. This means you're reflecting through the x-axis. So this one tells you you're reflecting through the y-axis, this minus sign. This minus sign tells you you're reflecting through the x-axis. So in other words, instead of going up, you're going down. So what this tells us is, let's look at this left curve. Now this left curve is actually y equals x cubed. The curve on the right is y equals sine of x. These are both examples of odd curves. So let's look at y equals x cubed. So we imagine instead of going to the right, we go to the left x units. So that means we're moving to the left. And it's telling us we're not getting the same thing, but we're getting the opposite thing. So we just go down instead of up. So if we went to the right by 1 unit, then you'd go up by 1 unit in this case, because it's 1 cubed. Now, if you go to the left by 1 unit, then we go down 1 unit. Now, this isn't drawn to scale, as you can see, because this is 5, and here we only have 1 and 2. So it's not drawn to the same scale. The x scale is not the same as the y scale, but you get the basic idea. However much you went up on the right, you go down on the left instead. Same idea with sine of x. If we go to the left, then we drop down instead of, if we went to the right, we went up. So this presents a natural question. Why do we call them even and odd? It has to do with the type of curves that you see when you look at y equals x to the n. So if y equals x to the n has an even exponent, then the graph has even symmetry. That is, the graph is symmetric about the y-axis. So here you can see a few examples. Y equals x squared, y equals x to the fourth, y equals x to the sixth. These graphs all have even symmetry. They're all symmetric about the y-axis. And because of that, whenever you see something which is symmetric about the y-axis, then it has the same kind of symmetry as y equals x to an even number. So that's why we call it even. For odd, then it's like y equals x to the n for an odd exponent. And we have some examples here. So if y equals x to the n has an odd exponent n, then the graph has odd symmetry. So it's symmetric about the origin. So y equals x to the 1, that's just the same as y equals x, of course. Y equals x to the 1, y equals x cubed, y equals x to the 5th. These are all symmetric about the origin. So any x to an odd exponent is symmetric about the origin. So if you see any graph which is symmetric about the origin, you say, oh, well, it has the same kind of symmetry as x to an odd exponent. So we call it an odd function, or say that it has odd symmetry. Now, the connection doesn't actually stop there. It's not just that it looks similar. Here's a fun fact. Any even function can be approximated using polynomials with even powers only. So in the graphs below, you can see a dashed graph here. This is y equals cosine of x. You can see it in all of these. Y equals cosine of x. All of these have y equals cosine of x. Cosine of x is an even function. And this even function can be approximated by polynomials with even powers. So for example, you can see here we have y equals 1 minus x squared over 2. That's this parabola which is opening downward. And you can see it sort of matches right around where x is equal to 0. Now if I want a better approximation, I just need more terms in my polynomial. 1 minus x squared over 2, that's the same that we started with before, 1 minus x squared over 2, but I just added in this x to the 4 over 4. This is 4 factorial. So 4 factorial is equal to 4 times 3 times 2 times 1. So the factorials are the product of all of the positive integers less than or equal to 4. And we put that in the denominator there. And this gives us a better approximation. Notice that this polynomial has only x to an even power. This 1 is x to the 0. 0 is even. So all of these x's have even powers. And that gives us this degree 4 polynomial here. If we add in an extra term, and by add in I mean subtract x to the 6 over 6 factorial, we get a better approximation. And the more terms that we add in, notice that in each step I'm keeping the same polynomial, but then I'm adding in one more term, x to the 8 over 8 factorial. Notice that this is an even polynomial that's symmetric about the y-axis, and therefore is the graph of an even function, and it approximates the function cosine of x better and better. And here if we have degree 10, it's even better, and if we have degree 12, it's even better. The more terms you add in, the better the approximation becomes. Now these terms didn't come from nowhere. There's a certain formula that you can derive which will tell you what the terms look like. But that's for another time. Instead, let's do the same thing for odd functions. In this particular case, we're looking at the odd function y equals sine of x, and you can see that's the dashed curve here that appears in all of these. And now I'm approximating it using polynomials that only have odd powers of x. So here we have y equals x minus x cubed over 3 factorial. Again, 3 factorial is 3 times 2 times 1. Here there's a 5 factorial, 5 times 4 times 3 times 2 times 1, and so on. And you can see that each step along the way, I add in another term, which is x to an odd power, and I get a better and better approximation. And the more terms that I add in, the better the approximation will be. And again, there's a formula that tells me what the next term will look like, and you can probably guess what it is based on the pattern. We're alternating between positive and negative, and then we just move to the next odd exponent, and we divide by that exponent factorial. And the more terms that we add in, the better the approximation becomes. Now there's a theorem as to why that's true, but that's, again, best left for another day. Another important property of functions is increasing and decreasing properties. So we say that a function is strictly increasing on some interval if the values of the function, the output values, increase in size as x moves from left to right. So here's an example. This again is y equals x cubed. Y equals x cubed. And as you can see, as we move from left to right, the output values are higher up on the y-axis. So this is strictly increasing. Now, if we want to write it using symbols, the defining property of a strictly increasing function is given here. The function f is strictly increasing on an interval I if whenever x1 and x2 are in I such that x1 is less than x2, it must be the case that f at x1 is strictly less than f at x2. So that's why it's called strictly increasing because we have a strict inequality here. If x1 is less than x2, strictly less than x2, then the output for x1 is strictly less than the output for x2. So that means we have a strictly increasing function. You can also have something like this, which is strictly decreasing. So here we have a function which is strictly decreasing. That means that as you move from left to right, the y values get smaller and smaller. So the defining property of a strictly decreasing function is that f is strictly decreasing on an interval if whenever x1 and x2 are in the interval and x1 is less than x2, then the output values are getting smaller. So that means if x1 is strictly less than x2, then the output for x1 is strictly larger than the output for x2. So as the x values get bigger, as the input values get bigger, the output values get smaller. So here we have x1 is strictly less than x2, so the output for x1 is strictly larger than the output for x2. The output values are getting smaller. Again, we call it strictly decreasing because we have a strict inequality here. And what that means in terms of the graph is that it's dropping. As we move from left to right, the graph drops. It gets further down on the y-axis. If we want to allow for occasional equality instead of strict inequality, we can weaken the condition. So we can say that a function is increasing or not decreasing, non-decreasing on an interval I, if whenever x1 and x2 are in I, and x1 is strictly less than x2, we may allow for equality. So we replace the strict inequality with a less than or equal to. So the values are not getting smaller. They might stay the same or they might get bigger. So here's an example of a non-decreasing function. It's constant for a while and then it starts increasing. Non-decreasing means that we're not increasing. So we might decrease and then we might stay constant for a while. So a function is decreasing or not increasing on an interval I if whenever x1 and x2 are in I, then when x1 is less than x2, x1 is the output for x1, f at x1, is greater than or equal to the output for x2, so f at x2. So that means the output values are not getting bigger. They might be getting smaller as you move to the right, but they might actually be equal, but they're certainly not getting bigger. So that's why we say non-increasing. Now, one important thing here is that this is on an interval. In order to talk about increasing or decreasing functions, we talk about an interval because we're comparing two values, f at x1 and f at x2. So we actually need to have an interval that contains at least two inputs. It's also possible to construct new functions from old functions using certain algebraic operations. If f and g are two functions that have the same domain, then you can add them together, you can subtract one from another, you can multiply them together, or you can divide one into the other. Now, in that case, you have to make sure that you're not dividing by 0. So the function f plus g is obtained by simply adding together the outputs for f and the outputs for g. Similarly, the function f minus g is obtained by taking the output for f and from that subtracting the output from g. And in a similar way, if you multiply f and g, You do that by multiplying the outputs together. And f divided by g is obtained by taking the output of f and dividing by the output of g. But again, in order for this to make sense, the output for g cannot be equal to 0. Another way that you can take old functions and make new functions is through something called composition. So f composed with g is a new function that's obtained by evaluating f at g evaluated at x. So in other words, we take the input x and we plug that into g. You plug that into g, and then that will give you a certain output. And whatever that output is from g, you plug that into f, and that becomes your new input. Now, in order for this to make sense, it's necessary that g at x is in the domain of f for every x in the domain of g. So x has to be something that you can plug into g, and that will give you a certain output. And whatever that output is, it needs to be something that you're allowed to plug into f. So g at x must be in the domain of f in order for this to make sense. Now, this leads us to a little bit of a warning. So the domain of f composed with g cannot be any larger than the domain of g, because you can't put any x into the composition unless you first put it into g, no matter what it might look like. And I'm going to give you an example that illustrates this. So here's our example. F at x is equal to x squared plus 3, and g at x is the positive square root function. So what happens if we look at f composed with g? So that means evaluate f at g at x. So the thing that's on the right, that's the thing that you evaluate first. So g is on the right. So you plug x into g, and then you compute g at x, and then you plug that into f. So g at x is the positive square root, so that's what you're plugging into f. So f evaluated at the square root of x is, well, the square root of x is our new input. Okay, that's our new input. How does f work? F is defined so that whatever the input is, you square it and then add 3. Now, in this case, in the definition, we used an x, but it doesn't have to be an x. It's just whatever is the input. So whatever goes here, you take that and then you square it and then you add 3 to it. So now our input is the square root of x. So you take this square root of x, and that's your input. So you take the input and then you square it and then you add 3. So whatever the input is, so blue blob, you square that blue blob and then you add 3. Well, in this case, our blue blob is the square root of x. Square root of x. So you square that and add 3. But of course, the square root of x quantity squared, that's x. So the composition, f composed with g at x, gives you x plus 3. Now, you might be tempted to think that the domain is all real numbers because I can plug in any x that I want, or I can plug in any real number for x that I want. However, the domain is actually the set of non-negative numbers because g at x is only defined for non-negative numbers. Now, this composition, I might think, oh, I can plug in x equals -1 there. -1 plus 3 is 2. But if I try to plug in a -1 into my function, my composition, the first thing that I have to do is I have to compute g at x. So if I put a -1 in there, then I'm going to have a problem because that's the square root of -1. So the way to compute the composition is first you compute, so step 1, you compute g at x. And then whatever that is, take that into step 2. Evaluate f at whatever number you get in part 1. So if it's not possible to do part 1, then you can't even start part 2. So you have to be a little bit careful about that because the domain of the composition can't be any larger than the domain of your original function g. It might be smaller. You might end up with a smaller domain because it's certainly possible that there's something that you're allowed to plug into g that you can't then, whatever that output is, you can't plug it into f. So it's certainly possible that you might get a smaller domain. That's possible. But you certainly can't get anything bigger.